All right, so just to remind you, the entire problem we're interested in is we want to define for irregular x. I just want to define an integral, right? So I talked about the Ito theory, the semi-martingale theory, and then I also gave the example of fractional Brownian motion, which unless h is equal to 1/2, it's not a semi-martingale, so it does not apply. So I was going to talk about the Young theory of integration. So Young proved in 1936 that F, B, and C alpha, G, B, and C beta. These are the alpha and beta Holder spaces with alpha plus beta greater than 1. Then FBG exists as just a standard Riemann-Stieltjes integral. So I'm going to give a proof of this using dyadic partitions. So using dyadic partitions, we can show this. So you show that so Young showed for any sequence of partitions with a mesh size going to 0. But I'm just going to do dyadic because it's just a bit easier. And note, by the way, before I prove this, just a note. As a corollary, we have that exists as Riemann-Stieltjes if f is C1, say with bounded derivative at least, and x is in C alpha for alpha greater than 1/2. So in the FBM case, that would be for FBM with h greater than 1/2, the positively correlated increments. Okay. So let me give a proof at least for dyadics. So by that I mean, consider TIN is I over 2 to the n for so we're just taking a dyadic partition of, say, the interval 0, 1. I'm just doing it over 0, 1 for convenience. So this is, let's say, so on just the interval 0, 1. Okay. All right, and then let's define IN. Two to the n minus 1. F of TIN. G of TI plus 1 n. This G of TIN. Okay. And basically, we just want to show that the limit as n goes to infinity of this guy exists, right? So standard technique, we just create a series and then show that the series is summable, right? Which is where the dyadics come in, from geometric series. So you have, say, I sub capital N with I sub 0. All right. Yeah, let me just set N equals 0 here. Not a big deal, but N equals 0 to capital N of I sub N plus 1 minus IN. And then as long as the series here is summable, then we have a limit for this guy. Right? So pretty standard technique for problems like this, but. Mhm. No, and not, you have to have, either this result or one of them be bounded variation or something like that. No.
So I sub N, okay, that's just a telescope inside. Okay, so.
Yep, I'm just. No, just telescoping sum. The big N is the thing that we're setting to infinity. And we just want to show that that sum is convergent. So the reason why we used dyadics here is just, it's easy to write IN in terms of the partition of IN plus 1. So we can write that IN is equal to the sum this. And then we can just write it in terms of the N plus 1 and then add and subtract. And then we have U of T 2I plus 2, the N plus 1 minus G of T 2I, the N plus 1, right? So I just write that in terms of the next partition, and then we can just add and subtract. And we end up getting T of 2I, N plus 1. So just adding and subtracting. Okay. So that's our IN. And then let's write out an expression for IN plus 1. Let me erase over here. Start IN, and then we can write as to the N minus 1. And then so I'm just splitting it up into the 2 I's and the 2I plus 1s. Okay. And then we can subtract these two. We get is equal to this increment here. Yeah. Just subtracting everything, and then we can get the bounds. In the Holder continuity of the alpha norm of F times the beta norm of G. Just using the Holder continuity assumption. And we can just evaluate this as a geometric sum as alpha G beta divided by that 2 to the n alpha plus beta x 1, which if alpha plus beta is greater than 1, we have that the series is summable. Okay. Yes.
But your original definition of I on the right, you're basically taking a partition that's white is like behind the
Exactly. Exactly. And then I just added and subtracted the in-between parts. Yep. That's right. Which is why the dyadics are really nice. It lets you relate the sums on them very easily like this. Yep. So Young integral exists at least for dyadic partitions, and then you can show additionally for all partitions with mesh size going to 0 that the Riemann sum converges. Okay. So any questions on this proof before we go on?
If you were trying to show it for a different, that was done in a different sequence for it.
It would be a lot harder. Yeah. I mean, it was an entire paper, a lot of bounds. And I mean, it was done in 1936. There wasn't a lot of, it wasn't anything, too fancy. It was just a lot of just analysis. Right. But yeah.
It would be never be the same except for the really last step. Or no, you have one embedded in another or something like that.
Yeah, if you do like refined partitions, you can do something like that as well. But yeah.
And what are the exponents? We have 2 to the alpha plus what is in the bottom?
This is 2 to the alpha plus beta, and this is 2 to the n times alpha plus beta minus 1. So all of this is a constant, and then as long as alpha plus beta minus 1 is positive, we have a geometric sum, right? Mm-hmm. Mm-hmm. Maybe, sure. Mm-hmm.
Upper parts, lower parts, upper lower part that is improved by the expert.
Mm-hmm. Sure. I mean, there's all sorts of ways of proving this. It's very, very classical stuff, but I just was giving one. Yep.
Same here with the demo case, like you have a sequence in the middle LP and another one use some kind of alpha, put them together and add them. And the condition is that one of the keys, one. Here, okay, as long as it's bounded by something, then take larger power, it doesn't matter.
Yeah, so
Turn to angle little L, P and little L, Q.
actually, in the original paper, he was doing it with P and Q variation, and then he just had 1 over P plus 1 over Q greater than 1. So it's a very, very similar idea. Yeah. All right. So very classical theorem. So this handles the H greater than 1/2 case, or for alpha, if your path is alpha holder for alpha greater than 1/2. And this is the first, like the first example of, or like the first or 0th case of a rough path.
Eventually come from focus and focus.
Yep. Yep.
Saying you prove that it really exists.
Mhm.
You say regular exists, so for what? You said you go to 0 and minimize. So it must be, it exists and has some property.
Well, it exists as a Riemann-Stieltjes integral, right?
Find it to 0 and then it's good.
It does exist. It does not satisfy certain properties, though. We'll be getting to that very, very shortly, actually. So a rough path is actually a definition of an integral that satisfies 2 properties. Okay. Yes. If alpha plus beta equals 1, there's cases where it's true and there's cases where it's not. This just doesn't, the argument here doesn't work. So for the exactly alpha plus beta equals 1, you can come up with some counterexamples. So one really easy case where you can be as irregular as you want would be if the support of F and G are disjoint, then you can be as irregular as you want and it'll exist as a Riemann-Stieltjes. Then the answer is 0, right? Right. So,
So this, like we're saying, what is a series converge on the boundary of a discrete conversion? Well, it's very complicated.
yeah. All right. So we've shown the existence of the Riemann-Stieltjes integral. Now let's go to the alpha less than 1/2 case, and let's go to the first non-trivial one. So for alpha greater than 1/2, we have Young theory. Young theory, which is the first order or the trivial version of rough path theory. And remember, for FBM, your Holder continuous for all alpha less than H. So for H greater than 1/2, we can just use Young theory. For H equals 1/2, we can use semi-martingale theory. For H less than 1/2, we need something else. So the first non-trivial case of this is going to be alpha in 1/3 to 1/2. Okay. So let me do a computation of, all right, we want to define. So if X is in C alpha, we want to define this, all right? So in particular, one thing that we want this to satisfy, or there's a couple of things that we want this to satisfy. First of all, we want it to satisfy, so we want it, A to B plus integral from B to C. It's the integral from A to C for A less than equal to B, less than equal to C. Okay. But so we wanted to satisfy this, which by the way, is Chassel's relation. If you guys didn't know, this was Chassel's relation. I don't know why it needs a name, but it does have a name. Someone wanted to stamp their name on it. Let me. It's French. So we wanted to satisfy that, and then we also want it to be linear, right? So using these two things, rather than having to define this for all F, yes? Linear in the integrand. So like C times F, we should be able to pull out a C. Like F1 plus F2, we should be able to split it just as a linear functional. So the idea of RepPass is rather than having to define this for all F, we can just break it down and find really what is the issue, what is the thing that we need to define, and it ends up being an iterated integral. And I can show you using a computation where this iterated integral comes from using this. All right, so we can take a partition, say, Yep. But for this, for Brownian motion, we don't have that it's alpha holder for any alpha greater than 1/2, right? But we do have that it's alpha holder in this range. So this does apply for Brownian motion. It applies for FBM with H between 1/3 and 1/2. That, right? So we take a partition P and we write it's equal to the sum. Yeah. So we can take this partition, split our integral over this partition. And then if F is smooth, so I'm assuming F here is smooth. See at least C1, but say C1, maybe more regularity depending on the regularity of X, but we can do a Taylor expansion of F and have that F of X of S is equal to F of X of TK plus F prime of X of TK times, actually, let me write it out here. F prime of X of TK X of S minus X of TK plus some remainder term. That is TK plus 1 minus TK to the 2 alpha. Okay. Just using standard Taylor theory. All right. So then we can plug that into the expression we have above. And we end up getting that this guy is equal to of F of X of TK, integral from TK to TK plus 1, plus F prime of X of TK, TK to TK plus 1 of X of S minus X of TK, dx of S, plus a remainder term the 2 alpha times the integral TK plus 1 dx of S. Okay. So what we've done here is rather than defining it for all of F, let's see what things we can make sense of in here. Surely this is okay. This is okay. We know what f of x of tk is. We know what f prime of x of tk is. We can just, define this as x of tk plus 1 minus x of tk. It's the same thing here. Thus giving a remainder of the power of 3 alpha. The only thing here that we don't know is this guy. That iterated integral is the only thing that we don't know how to make sense of. So let me just write this over here. So we have that. And plus f prime recall that 3 alpha is greater than 1 because we are assuming alpha was greater than a third. So that remainder term goes to 0. Okay, as the mesh size goes to 0. So the only thing, so the key insight here is rather than defining this integral here for all f, we just have to define it for f being the identity. We just have to define the iterated integral. That's rough path theory. Can we define that iterated integral? And if we can define that iterated integral, then we can just take this as our definition of integration, which if you notice, it's basically a Riemann-Stieltjes sum, right? If we didn't have the second order part, we would have this Riemann-Stieltjes sum here. It's just a Riemann-Stieltjes sum plus a correction term, plus a regularization term. We cannot define, so if we ignored all of this, yes, we can, this limit, we don't know it would exist. In many cases it wouldn't. But if we include this extra term, then the limit does exist. The limit does exist when we include the second regularization or correction term, including the iterated integral. The limit as n goes to infinity and as the partition size goes to 0. So I'm taking. Yes. So that's a sequence of partitions Pn where the mesh size is going to 0. Yep. That's because it's 3 alpha is greater than 1. Huh? No. The first and the second exist together. The first term by itself will not converge. The second term by itself will not converge. First plus second together converges. But yeah, I mean, that's a very good point. It's really correcting. It's really adding something to the Riemann-Stieltjes integral that makes it converge. And it's really, we have to keep track of this kind of area process. You can think of this as an area process of X, right? You can think of this as extra information on X. So, there's a lot of, there is. So there's the Levy area, which is just the integral of, if you have two independent Brownian motions, the integral of x1 dx2 minus the integral of x2 dx1, it traces out an area, and that integral is the area of the region. Yep. So it really is an area. And the second term here, this iterated integral, studying this is what rough path theory is about, is studying iterated integrals. Okay.
The sum and everything in that sum, like you have to put a brace.
Yeah, so everything's inside.
To limit the sum, it's everything.
Yes. Everything in there is in the sum. Yep. So the point is we can reduce defining the integral of f of x to just defining this iterated integral. Okay.
You keep saying that if you show the second term converges, you got it, but actually, if the first term doesn't converge, so that actually show the whole thing.
Well, I mean, this guy right here, this guy converges. The error term converges.
So, wait,
Yeah. Yeah, we can forget about this because 3 alpha is greater than 1. No, just this thing is circled. This is the iterated integral, x dx.
So that, then the rest of the previous thing.
So then this entire thing exists if this exists and satisfies certain properties. Okay.
The second one is there.
If alpha is greater than 1/2, well, we can expand this out, right? It's not going to change anything. So if alpha is greater than 1/2, we can include this in the sum, the second component in the sum. But the limit will just be the limit of this guy. Yeah, that's right.
Just to make sure, you're saying you almost define that it's great, iterated integral, so that the sum of the first terms will converge.
That's right. Yes.
We have to define that.
Uh-huh.
Then we conclude the right-hand side. converges.
Yes,
Can't do it without first. That would determine the intent.
exactly. So we just have to give a definition of this. That makes sense. Okay. So, yeah, let me define a rough path then. So one point about rough paths is that the second order term, that iterated integral term, is non-canonical. So let me just define definition. Say, given a signal x in C alpha of 0 to t to say RD, a rough path above x is a map say from what's called the two simplex. The two simplex is just or as somebody got angry at me and said, when I mentioned the two simplex, someone got angry. They're like, you mean the triangle? So it's a function from the triangle to RD. So don't get too worried about that. Just map from RD to, so a pair RD and RD by D. So matrices, so that such that we have, so basically we consider ST maps to X1 ST, X2 ST, and we also satisfy the following three things. X1 ST is X of T minus X of S. The second thing is that the soup over T not equal to S of X ST2 or T minus S to the 2 alpha. It's finite. So that's just a regularity condition, which should hopefully have made sense where that came from before. And the final one is what is called Chen's relation. And you guys are going to have a lot of questions on what is Chen's relation, but tensor product CUT 1. That is called Chen's relation. It's the third one. That's ST minus SU minus UT is SU and then UT. So that third relation is Chen's relation, which is one thing we have not talked about yet, but so here we have that S, U, and T are in the 3 simplex, just meaning S is less than equal to U is less than equal to T. That's correct.
Doing that last one, well, now that's a tensor of the.
Yep.
That relation, that's the tensor of the 2
Is these matrices. That's right. One. That's correct. SU and then UT. That's right. One really important thing I do want to mention about in this definition of rough path here. Do you see any iterated integrals whatsoever in this definition? No. There's nothing in here that is an iterated integral. That's very important. It's very important. X2 here just is a matrix. That's all. And it satisfies these properties.
Not quite.
Yeah, not quite. So the X2 is not quite uniquely defined in terms of X1, but almost. It's defined uniquely up to the increment of a 2 alpha function. So I'll talk about that in a second. Does there exist a unique X2? And the answer is no. But one thing I really do want to emphasize is that in this definition of a rough path, there is no iterated integral. There is no iterated integral here. Once we have this definition, okay? Once we have this definition, then we can define is defined as, and it's really important that you read that definition the right way. Once we have a second order object, the X2, then we can define the iterated integral as X2. Not the other way around. We don't define the iterated integral first, we define the X2 first, and then recover the iterated integral. And as you had said, it actually is not, the X2 is not uniquely defined from X1, okay? So the reason why is because there's no canonical choice of an iterated integral, right? So for the alpha greater than 1/2, we can just do a Riemann-Stieltjes integral. However, when we're very irregular, we have to make a decision. So for example, if you just think about Brownian motion and the Stratonovich integral and the Ito integral, this is a choice you have to make that give you 2 different answers, 2 different results. It's a choice. So you have to make a choice here of integration theory of this X2.
Always exist.
Yes, they always exist. That's right.
Choice.
Yep. So let me give one example of a perfectly okay choice in dimension D equals 1, okay? So if D is equal to 1, define X2 ST as, say, X of T minus X of S squared over 2 as a definition. That is not coming from any kind of limit. That's not coming from anything at all. I'm just algebraically defining X of T minus X of S squared over 2. And we can check that it satisfies these properties, right? Certainly satisfies this if X is alpha holder, and when we square it, it's 2 alpha holder, right? So it certainly satisfies the first one. The second one, the Chen's relation, it's a little bit more tedious to compute everything. So it satisfies yes. Yep. Yep. So, you know, in dimension D equals 1, the rough path theory is sort of trivial in this way, right? We can just define X squared by 2, which is, we go through all of this nonsense and we get the answer that your freshman calculus student would give you. What is the integral of X dx? Well, it's X squared by 2, right? And that's a perfectly acceptable definition of an integral. And the point here is that we're algebraically defining it. We're not defining it through a limiting procedure per se. I mean, you can define these through certain limiting procedures. And in general, the way you want to define the a rough path is through some limiting procedure. These are called geometric rough paths. But at least for right now, we're just algebraically postulating that the iterated integral is just X squared by 2. Yes.
If it satisfies the condition, and it cannot satisfy the Charles condition,
Oh, Chasles, you mean?
yeah, let's see, it's going to
Oh, the difference here is that we have a dependence on the S inside the integral, right? The other one we didn't. Or sorry, this should be dx of R. Sorry about that. Dx of R. Here we have an S as the limit of integration and also inside the integrand. But the point is the Chen's relation is sort of the version of that for these iterated integrals of this form. Okay. Yeah.
Be fair to say, find integral by the final empirical calculus, that we don't tell you what the derivative is. We just say it's an antiderivative,
Yes.
but we don't say what an antiderivative is.
Yes. Yes. No, I mean, that's exactly it. We're just postulating. We're just postulating it.
So proving that every continuous function will be an integral, then we would say we take something that satisfies some algebraic condition, and that's what we're going to call.
Right. It's like the it's called the Newton integral, right? So yeah, so one thing, as I said, we're just postulating this. I don't want to overemphasize the postulation part, right? Because this condition, this Chen's relation, really is quite restrictive. Okay, so we don't have a unique enhancement to a rough path, but the Chen's relation fixes what the rough path is quite strongly. So in the sense that if we take two different rough path lifts, they're going to differ only by the increment of a function. Okay, so let me just write that out. So first of all, it's the first fact. If X1, X2 is a rough path above X, and F is a 2 alpha holder function, okay, then X1, X2 plus F of, say, ST is a rough path above X. Okay. So given any rough path, you can always add the increment of a function and get another rough path. And if you can always add a constant, right? You can always add a constant. That's exactly right. You can always add a constant. You can always add a f of t minus f of s. And as a matter of fact, they all differ by an f of t minus f of s. So if you take two of them, if you take x2 and an x2 prime, and you look here, so another fact, and you can check because this is 2 alpha holder, so it satisfies this, and the sum of 2 alpha is 2 alpha, right? And then for this one, this thing on here is like a difference, it's like a triple difference, right? Exactly. It just gets rid of that, gets rid of this second part here, right? And then, conversely, right? The derivative of a constant is 0. And if the derivative is 0, then it's a constant. You can think of the same thing here, right? This f of t minus f of s. So another fact is that if x1, x2, x1, x2 tilde are two rough paths, then x2 minus x2 tilde is equal to f of t minus f of s, where f is 2 alpha. And you can check that again just from Chen's relation. Similar thing of just the derivative of a constant is 0, and if the derivative is 0, then you get a constant, right? So if you think about Ito integration versus Stratanovich integration, they're both the same thing, except for a t minus s, right? And that is your increment. And one really important thing, as we had said before, if f was a smooth function of your process x, you wouldn't expect it to be 2 alpha holder if x is only alpha holder. So your f is not going to be a function of your path, in generally speaking, right? So you want to think of your f as just like the increment of something else. It's sort of as you were talking about, like the plus c in integration. So
This was Chen's condition. It looks something.
yeah,
Some boundary or some cohomology or some boundaries. This is sort of like can differ by a boundary.
mm-hmm. Yeah, so basically where this comes from is it comes from the signature of a path. So the signature of a path is the collection of all iterated integrals. And this takes values in the tensor algebra, which, just you think of it as RD by D, then cubes and things like that. And then really Chen's relation in full generality just says that the increments of this signature just are multiplicative. I'll talk about that tomorrow, but tomorrow I'm going to spend a lot on that Chen's relation and where it comes from. Or 1/2 T, right? But yeah. So that's for Ito versus Stratonovich for Brownian motion. And there is a definition. So there's what's called the geometric rough path above a rough path, which is unique. And that is somehow seen as like the canonical version. Okay. So, a priori, when you look at this definition of rough path, you can write down whatever you want for X2, right? But that's sort of true, but as you see here, it's not quite true. And then when we talk about the geometric rough path, which is actually how you construct a rough path above X, then it becomes a lot more clear that this is not, it's not as arbitrary as you want. You can always add these increments of functions, but that doesn't really change. You construct it using kind of, basically you construct rough paths as a closure in the rough topology of smooth paths. So we'll talk about that later. Yep, it is arbitrary. You can choose whatever if you want, and it would be a rough path. Yep. You can choose f equals to 0, which is you have the geometric, and then an f equals 0, which is somehow the canonical version. Yep.
Argument against this activities.
So one thing I would say, at least for the geometric, so the Stratonovich integral corresponds to the geometric rough path, right? So yeah, so basically you can enhance a Brownian motion with an Ito integral or with a Stratonovich integral. The thing about the Stratonovich is that is the geometric one. So it behaves well, as in like there's a fundamental theorem of calculus, the integral of x dx is just x squared by 2 and all of these things. So it's nice there. And by the way, the Stratonovich integral converges almost surely, which is really nice. You don't have it's not a martingale, but it does converge almost surely, which is nice. But I would say the arbitrariness is inherent to the theory. The point is, these are too irregular in order to have a truly canonical definition, right? So one thing, by the way, is if you were to look at this and say alpha was greater than 1/2, like in the Young theory, and we were to look at this, if f is in 2 alpha, for alpha greater than 1/2, so then 2 alpha would be greater than 1, and the f would be a constant. So in that case, we really would have a canonical definition of a rough path above an alpha holder function for alpha greater than 1/2. But for the alpha less than 1/2 case, I think inherent to the theory is that it's arbitrary. I don't think you can get away from the arbitrariness. It's just too irregular to not have some level of arbitrariness. We have to make a choice. And rough path theory says like, this is kind of a bookkeeping mechanism for the right choice to make. The right choice to satisfy these properties. And if you make a choice that satisfies these properties, then you're able to solve, rough differential equations, define this integral, do all this other stuff. But at the end of the day, you have to make a choice. And there's no way of getting around the arbitrariness. Yes. It's a very important theorem, and it comes from basically you take a smooth approximation of your X. You consider not just the first component, but a topology on both components called the rough topology. Then you take the limit in the rough topology that keeps track of these iterated integrals. And then you're able to converge. The rough paths that you get from these are called the geometric rough paths.
What about other figures like this? Yeah, so once you do one app, then you know the complete parameter, because every other one, you just make it different. Some other app.
Yep.
So you parameterize by C2 alpha.
Yep. Do you have a question?
Reasonable conditions that can uniquely determine that, like the application that's not so consideration.
So again, it's a choice that you have to make. And generally speaking, the application will determine what choice you want to make. I will say the geometric is unique, and that's generally seen as the canonical choice. But you know, so you could do the geometric for example, for Brownian motion was the Stratonovich integration, and then you can just add the increment of 1/2 t to get Ito, which gives you all this martingale theory. So if you want to deal with martingales, you do the Ito. If you want to deal with, you know, almost sure convergence, all this other stuff, you would deal with the, well, I mean, it's all in rough path, it's all almost sure. But if you want to deal with the martingale, you deal with the Ito. If you want to deal with these transformations, like a fundamental theorem of calculus and stuff like that, you deal with a Stratonovich.
So that's what I'm thinking. That you can talk about it, if you want to take this formula and use the other. So beyond that, there are other conditions that will help you determine.
As I said, in general, the geometric is going to be the main one that we care about. Because again, one thing to think about is rough path, this is all done pathwise. There's nothing probabilistic here. Given that there's nothing probabilistic here, you know, things like martingale or whatever in general, this just doesn't see that, right? So it's going to be harder to, you know, talk about any probabilistic properties. So everything here is done just with functions, with paths. All right.